Hello everyone, welcome back. It's time today to talk about the normal distribution. I'm sure some of what we're going to talk about today is a little bit of review, but it's going to be an important part and an important building block for how we're going to get into talking about um, inferential statistics and is fundamental to our understanding of how statistics work. So, why the normal distribution? I like this. What do the weights of baby sharks and blood pressure have in common? They follow a bell-shaped curve. Data tends to center around a central value with no bias left or right. Um, these histograms are pictures of data that roughly follows a bell-shaped or Gaussian model or normal distribution. Essentially, normal distributions are just strangely really common. Here's a bunch of them. And I could add more. I like the parts you buy at Home Depot, normally distributed. The thicknesses of your wood, normally distributed. All kinds of things that are supposed to be one thing, right? The actual measurements in them are centered around sort of some kind of roughly normal distribution. Here's a picture of women's shoe sizes. Kind of fun, normally distributed. A little history, because some of us love to geek out. If you don't like to geek out, don't worry, this won't be on any exams. The normal distribution for data was discovered around 1720 by Abraham de Moivre, a French mathematician and a friend of Isaac Newton's. So it's been around as long as basically physics. Belgian mathematician Adolphe Quetelet had the idea of using the curve as an ideal histogram to which histograms for data could be compared. So he sort of saw it as a way to approximate actually how we thought about data. And famously, German Carl Friedrich Gauss, born in 1777, is also often credited for discovering the curve. It's called a sort of a Gaussian curve. So very early on, there was this idea that you could anticipate or approximate what might happen with data, right, using something like this normal distribution as a kind of way to predict what would happen. So we study this theoretical normal distribution because it approximates many natural phenomena so well that it serves as a standard reference for many probability problems. And data analytics depends on your understanding of distributions, among other things, but understanding that distributions underlie how data behaves. I like to say real world data is messy. We rarely get, right, the sort of perfect picture we'd like. And so amongst that messy real world data, the normal distribution does a reasonably good job of approximating much of how real world data behaves. And when our data doesn't behave normally, it's worth taking note of how it does behave. So the normal distribution, right, is a type of continuous probability distribution for a real valued random variable. Here's the general form of its probability density function. Note, because of that E in there, it's not actually integratable, which is why we're going to give you some approximations of what the area under the curve looked like, but I don't expect you to tap into your second semester of calculus to do anything with this formula. And if you don't have a second semester of calculus, no problem there either. I don't expect you to memorize this formula or actually ever even use this formula. But, again, sometimes it's nice to know that there's some math behind what we do. Otherwise, it keeps me up at night wondering if there's math behind what we do. So instead of having to memorize a formula, I think that this is a handy reference that you'll use sort of much of the time as you think about, right, the normal distribution. The normal distribution then allows us to come up with what the probability of something is in terms of how many, right, sort of standard deviations. So this is a useful approximation of the normal distribution. and is something that you can use as a reference point to help you understand how the normal distribution relates to probability. So it tells us that, right, about 34% of the time, something will lie, right, between 0 and 1 standard deviations of the mean, which is handy. 68% of the time, it'll lie between plus or minus 1 standard deviation of the mean. To get to 2 standard deviations, right, we get a little bit of extra stuff. So that sort of suggests that taking one of the things that we talked about, women's shoe sizes, what was the average? Something like an 8, it looks like. So, right, you say that the mean is at that 0, 8, and, right, nearly 68% of women's shoes are going to be sold between plus or minus that size 8. Nearly 95.4% of women's shoes are going to be plus or minus 2 standard deviations of that size 8. Another handy way to think about this also is that 50% of observations lie below the mean, and 50% of observations lie above the mean. So, if you wanted to know what proportion of observations lie below 1 standard deviation above the mean, you have roughly 50% plus an additional 34% or 84%. So both of those sort of facts about a normal distribution and kind of what that area under the curve represents will help us use the normal distribution to calculate probabilities. And so then we can turn to some real-world data and think about how that normal distribution pertains to this real-world data. So what percentage of observations are between 7.6 and 12.4? Well, that's roughly plus or minus 1 standard deviation from the mean, right? With the standard deviation being 2.4. So the mean here looks like it's at 10, so 10 plus 2.4 is 12.4, 10 minus 2.4 is 7.6. So that's 1 standard deviation, so we know it's going to be about 68%. 2.8 and 17.2, that's 3 standard deviations. We're going to cover about 99.7% of the curve. We can look at subsets of this too. What percent of observations are between 12.4 and 14.8? That's between 1 and 2 standard deviations, about 13.5%. What percent of observations are between 2.8 and 7.6? Right, that's between 3 and 1, about 16%. I like to keep one of these handy because it allows you to go between 3 and 1 is about 13.5% plus 2.5%, or between 1 and 2 was 13.5%, and get those kinds of answers. All right, next we're going to go ahead and use a normal distribution and use it to help us estimate the probability of something. So here, our question is that the average time to complete maintenance on an equipment part has been recorded for years, with an average of 15 minutes and a standard deviation of 5. It follows a normal distribution. Your boss bets you $100 that the next maintenance action takes at least 27 minutes. What is the likelihood that your boss is right? So we can use this normal distribution, a standard normal distribution, to map our specific normal distribution. So normal distributions, the graph you just saw, are given to us in terms of z, which has a mean of 0 and a standard deviation of 1. it's a kind of scaling like you would have on any map that we can scale against any, right, sort of real world values. So here our average is 15, that's been put on that 0. We can scale one standard deviation is up 5 from 15, so we would want to put it at 20. 2 is at 25. 3 is at 30. Minus 1 is at 10. 5 for minus 2, and 0. The boss is taking a bet that it's going to be 27 minutes, which is right about here. Seems highly unlikely, doesn't it? The probability the boss is right is only that area, that teeny tiny area left over under the curve. We can calculate what the z is there using this formula, or we're going to just let the computer do it for us in a second, but we can map our z x minus mu over sigma. Here it would be 27 minus 15 over 5, which is going to be 12 over 5, which is going to be 2.4. With that, we can go to R and use R to help us calculate, right, the probability of being in that little tiny tail. All right, here we are in R. I've set it up for us here. We can use this formula P normal to calculate. It takes the form x, 27, average, mu, 15, and sigma, 5. Let's go ahead and run that. This 99.18, which is all of the area to the left. Since we want all the area to the right, we could take 1 minus that p normal, or we can let the computer do it by telling it that we want that the lower tail is false, and that will give us what's left over, or 0.008, right? Slightly less than 1% chance that the boss is right. Oops. The next question we're going to have is to create confidence intervals for 90%, 95%, and 99%. To do that over here in R, we're going to want to use the formula Q normal. So we can type I did want to add, we could have, because we've already mapped it in terms of z, we can go ahead and find the same information using P normal of our z of 2.4, our mu of 0, and our standard deviation of 1 should give us the same number. The next thing that we're asked to do here is to create confidence intervals. We're going to go ahead and use R to create these 90, 95%, and 99% confidence intervals. We can use the Q normal function to create our confidence interval for our upper and lower bounds. For a 90% confidence interval, that suggests that there's about 5% left over in either side. So we're going to put 0.05 here. Our average here, which is 15, and our sigma, which is 5. We can use the same for the upper bound with that lower tail false. All right, from there, we also can run our 95% confidence interval, which leaves 2.5% in each tail, and our 99% confidence interval, which leaves 0.5% in each tail. We're going to go back to PowerPoint and label our graph. All right, back here in PowerPoint, we can go ahead and label our normal distribution with these confidence intervals. So our first confidence interval of 90% is going to be around 6.7, 6.8, up to 23.2. Our 95% confidence interval is going to be from about a 95% confidence interval is roughly plus or minus 2 standard deviations. It's actually plus or minus 1.96 standard deviations. So, but we could say plus or minus 2, 5, or 25, or we could use the more precise numbers that we got from that effort, which gives you 5.2 and 24.8 and 99, which is going to be over here at about 2.1, somewhere between, right? And up here at 27, right? So what that's essentially telling you, right, is that all of this area under here represents 90% of the observations. If we push it out a little bit more, it represents 95% of the observations. If we push it out even more, it represents, right, 99% of the observations. So that's what we're getting out of that confidence interval. It's that all of those observations, right, everything that's between 6.8 and 23.7 is where things are going to be 90% of the time. Between 5.2 and 24.8 is where things are going to be 95% of the time. So that's how we use the normal distribution to understand, right, and predict what's likely to happen in the future. So now that we know how to use a normal distribution to predict probability, we're going to go ahead and take a look at some common language and then take a visit to the central limit theorem to use that knowledge to understand the behavior of averages and predict things about the average from in a sample.